Hello and welcome to my presentation. My name is Ihan Chen, and today I will be presenting on our work entitled Direct Image-Based Traffic Junction Crossing System for Autonomous Vehicles. This work is done in collaboration between the Technical University of Munich and BMW. I will begin by going through the motivation for this work. The task of traffic junction crossing is generally viewed as part of the standard navigation task of an autonomous vehicle, which is tackled in a three-step process. In the first step, GPS is used together with onboard vehicle sensors to localize the vehicle within a high-definition map. Then, the sensor data and the map are used to build a complete model of the surrounding environment. Finally, the system uses this model to decide whether the traffic junction is safe to be crossed. While the approach allows for the system to be developed separately due to its modularity, it also causes the final decision-making step to be very sensitive towards localization error and error in the construction of the environment model. In this work, we would like to tackle the problem by proposing a two-stage system to perform decision-making for traffic junction crossing using the direct perception approach. This means that the system infers whether a traffic junction is safe to be crossed directly within the image space without the need of an environment model or maps. Here, the term safe refers to both being collision-free and complying with traffic rules. Figure 1 shows an overview of our two-stage system. In general, the system takes in camera images and infers the decision on whether to cross a traffic junction. When the traffic junction is safe to be crossed, the system should infer the decision go, meaning that a vehicle can cross a traffic junction. When the traffic junction is unsafe to be crossed, the system should infer the decision stop, meaning that the vehicle must stop prior to the traffic junction. I will introduce each component of the system in the next few slides. The first stage of the system is responsible for extracting high-level information from camera images. Information such as traffic light state, presence of stop sign, and instance flow are extracted with the help of convolutional neural network-based detection models. Two CNN-based detection models, the ITSC and fMRCN, are used in this work. The development of these models are not part of this work, and they are used as is to extract information from camera images. The information extracted from the first stage of the system is passed on to the second stage to infer the final decision on whether to cross a traffic junction. Before being used for decision-making, the information is first represented as affordances. We follow the definition of affordance from the work by Sauer et al., where affordance is defined as the property of the environment that limits the space of possible actions. For example, the traffic light state is an affordance, as its three different states, red, green, or off, dictates the action that a vehicle must take. In this work, we explored three different affordances as shown in Table 1. They include traffic light state, stop sign relevance, and collision with dynamic object. These affordances are obtained based on the detection outputs from the first stage of the system. Detailed equations and explanations on how the affordances are obtained can be found in our manuscript. Once the affordances are obtained, they are used to infer the final decision on whether to cross a traffic junction. We model the decision-making process using a Bayesian network as shown in Figure 2. Here, the three affordances and the final decision, or action, are being modeled as random variables within the Bayesian network. In general, the Bayesian network aims to model the following three situations where a vehicle needs to brake as it approaches a traffic junction. Firstly, the traffic light at a traffic junction turns red. Secondly, there is a stop sign at the traffic junction. Thirdly, there is a potential collision with another traffic participant approaching the traffic junction. Further information about the conditional probability distribution, as well as the final decision or action probability, can be found in our manuscript. Besides the decision-making system itself, we also included a system activation module in this work. It acts as a trigger that activates the system in the presence of a traffic junction. The module detects the presence of a traffic junction by means of semantic segmentation. Semantic segmentation is the task of assigning each pixel within an image to a predefined semantic class label. The presence of a traffic junction is determined by assessing whether the segmentation result contains the traffic junction label. In order to evaluate the system presented in this work, we introduced the frame of no return, or FNR. FNR refers to the frame within a video where the decision for a task is finalized, and any decision change after it will have no effect on the outcome of the task itself. For traffic junction crossing, FNR is the frame in which a vehicle must decide whether to cross or brake prior to the traffic junction based on a predefined deceleration profile, A-stop. Here, A-stop can be viewed as a vehicle's driving behavior, where a higher value corresponds to an aggressive behavior and a lower value representing a defensive one. Assuming that A-stop is constant, a vehicle that decides to brake after FNR will not stop prior to the traffic junction, but rather somewhere within. Under this constant acceleration assumption, FNR can be calculated by identifying the frame where the distance to the junction based on a constant A-stop is equal to the distance to the junction based on current vehicle speed. This is represented by the intersection point between the blue and red curves in Figure 3. For our work, we fixed the vehicle speed to be the first speed value of a video sequence when calculating FNR. This is because the actual speed of the vehicle at each time frame already contains the decision of the driver whether to cross the traffic junction. By fixing the speed, we effectively removed the decision from the driver and assumed that the driver drove into the traffic junction blindly with constant speed. To evaluate our system, we performed experiments using the roughly 2 hours of unlabeled video sequence released by the authors of the Cityscapes dataset. The video sequence comes with vehicle odometry, which is required to calculate FNR. We extracted 69 shorter sequences of scenarios where the ego vehicle is entering a junction. They are then manually labeled as either safe or unsafe to be crossed. As the prediction output of our system is binary, we evaluated the performance of our system by looking only at the prediction accuracy for the action stop. The accuracy is evaluated for 4 different FNRs, which are obtained from 4 different A-stops. Furthermore, we also evaluated the precision of identifying a traffic junction to assess the system activation module. Here are the results from our experiments. Figure 4 on the left shows the prediction probability for the action stop for a single sequence. The 4 vertical dashed lines correspond to the different FNR obtained using different A-stop values. The prediction probability at the FNR is used to determine the final decision of a sequence, which in turn is used to calculate the overall accuracy of our system. Figure 5 on the right shows the overall prediction accuracy for 4 different FNR, which are represented by the different A-stop values. The x-axis shows the prediction threshold used to determine the final decision of a sequence, while the y-axis shows the corresponding accuracy of using such a threshold. From Figure 5, we can see that our system achieved an accuracy of 80% to 95% for different A-stop values, with the larger A-stop having a higher accuracy compared to the smaller A-stop. With smaller A-stop, the FNR is further away from the traffic junction, meaning that objects are further away and smaller in the image. This causes the detection performance of the CNN-based detection models to decrease, thus affecting the accuracy of the final decision. Better detection models for small-sized objects will be needed to improve the accuracy of the system at smaller A-stop, which is out of the scope of this work. Besides evaluating the decision-making system itself, we also assess the feasibility of the system activation module. As mentioned previously, this module uses semantic segmentation to detect the presence of a traffic junction. Since the extracted sequences used in this work do not contain ground truth semantic labels, we are unable to evaluate the results based on the standard mean intersection over union metric. Instead, we evaluated the precision of the module in identifying a traffic junction at different A stop, which corresponds to different FNR. We found that the precision drastically decreased for smaller A stop, highlighting the difficulty in detecting traffic junction at far distances. Figure 6 shows some qualitative semantic segmentation results, where the bright green area represents the traffic junction class label. Here is a video clip that visualizes the intermediate results and the final decision probabilities of the system. There are 3 sequences in this video, and each sequence will be paused briefly at the FNR. For each frame of the sequence, the original video will be shown on the bottom right, while the frame number will be shown at the top of the frame. The different FNR values will be shown together with the frame number. Moreover, the affordance values and the final decision probabilities will be shown on the top left and top right respectively. Please pay close attention to the decision probability values here. Finally, each frame will also contain the detection outputs from the first stage of the system. The first sequence is an uncontrolled traffic junction crossing, where the traffic junction is safe to be crossed. Here, the system correctly identified that the eagle vehicle will not collide with the passing vehicle. The second sequence involves a green traffic light, meaning that the traffic junction is safe to be crossed. The third sequence involves a red traffic light, meaning that the traffic junction is unsafe to be crossed. To summarize, in this work, we introduced a vision-based system for autonomous vehicles to decide whether a traffic junction is safe to be crossed. We modeled the decision-making process using a Bayesian network that obeys traffic rules and avoids collision with moving vehicles. We showed how information can be extracted from camera images and represented as affordances for the decision-making process. As the system is modular, it can be easily extended in future works to include more complex perception modules to address the limitations in the current system, and traffic scene occlusion, which is not covered in this work. With that, I would like to conclude my presentation today, and thank you for your attention.